So hopefully by now you've figured out some of the relationships between the settings we can control on the simulation and the gravity force and the velocity vectors on the planet and the sun. So I just want to really explicitly point out the things that are affecting these two variables, the gravity force and velocity. So first, let's talk about gravity force. I've turned it on so we can watch it, and I want to point out that changing the star's mass changes the length of this vector, so changes the strength of that gravity force. Changing the planet's mass also changes this, and changing the distance between the objects also changes this length of the vector. So I'm going to come over here and write that mass of the sun, mass of the planet, and r, this distance between the sun and the planet, and it's always measured from the center of both, so the center of the sun to the center of the planet. These should all be in our equation for the force of gravity. And this equation turns out to be m2 m1 over r times a constant g. m2 is the mass in the center, the bigger mass, that m1 is orbiting. So in our case, ms is m2 and mp is m1. And this should make sense because as we increase m2 or m1, the gravity force gets bigger, bigger, bigger. Makes sense because they're on top of our fraction. As we increase that r value, that distance, our gravity force gets smaller. That tells us, yes, it's on the bottom of our fraction. So this is known as the law of universal gravitation. And it kind of rules all massive objects in the universe. So any two objects have this equation that tells us the force of gravity between them. And you'll notice this is an action-reaction pair. One massive object has a force acting on the other one, and vice versa, that same object has the force acting on the other object as well. Okay, so we will be doing some calculations using this in the future. Okay, next up, let's look at the velocity vector. So I've turned it on our simulation, and I want to point out there are two settings that affect the velocity vector. So first, let's see what happens when we increase the star's mass. Watch that velocity vector closely. It's going to grow and grow and grow and grow and grow. Okay, so I'm going to write that down over here. We know that the mass of the star is affecting our velocity. Okay, now let me reset our simulation, and let me change the distance that the planet is from the star. Let me turn on that velocity vector again. Now let's watch what happens. Watch that arrow. It's going to grow, 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 grow. Okay, so come back over here. We know that the distance, that r value, remember, distance from the center of the sun to the center of the planet, is going to affect our velocity. Let me reset it again, just to show you that changing the planet's mass is actually not going to change our velocity at all. So we are not going to include that in our list over here. We'll talk about why in a minute. Okay, so it turns out that the velocity of an object orbiting another massive object is equal to the square root of that g constant that we just introduced times the mass of the sun. Remember, sometimes the mass of the sun will have m2 as its name. Remember, m2 is that center mass, and m1 is that smaller orbiting mass around the outside. And this is all going to be over this r value. Okay, remember g equals 6.67 times 10 to the negative 11th. Okay, so this is the equation for the velocity of an object that is orbiting another object. It does not depend on the mass of that smaller orbiting object, only on the mass of the sun and the value r.